In question of the day 7, you are asked to find, in the first part of problem 7, you're asked to find a derivative and then the derivative of that function, which would be the second derivative. So I've gotten this problem started. If I have made a numerical error, please notify me, but compare your work to mine. I've got the function f of x equals the identity function. In fact, I've got a multiple of the identity, 8x, times the exponential function base e, and e is being raised to the 7x power. So I've got a product of functions, and that's how I'm going to treat this problem using the product rule. I'm going to treat just like my fingers are showing there. I'm going to group together 8x, then the exponential function e to the 7x. And using the product rule, I'm going to write the first function down, multiply that function times the derivative of e to the 7x. And so I'm using the differentiation operator d dx to indicate that I will be taking the derivative, and that derivative will be with respect to the independent variable x. Then e to the 7x is multiplied times the derivative of 8x. And so here are those derivatives respectively. The derivative of e to the 7x by the chain rule is e to the 7x times the derivative of 7x, which is 7. So 7e to the 7x is the derivative of e to the 7x. The derivative of 8x is 8, and so notice that I've expressed this derivative is 8 times e to the 7x. So I'm already putting these this expression is going to identify that first derivative in good form. Multiplying 8 times 7, 56x times e to the 7x plus 8e to the 7x. Now I could group, I could go ahead and think of a like term in each of these as being e to the 7x, and by grouping factor that common factor e to the 7x out of the sum of these two expressions and work with 56x plus 8 and take the derivative, which will be the second derivative. I could do that, but I am just going to work, and I did work with these two expressions just like you see here. So the next thing I did, I've got 56x. I thought of that multiple as my first function, and e to the 7x is the 7. I'm approaching this problem, this product, just like I did the product of 8x times e to the 7x to find the derivative. So 56x is written down. I'm going to multiply times the derivative of e to the 7x, which is 7e to the 7x. I will multiply e to the 7x times the derivative of 56x. That'll be 56. So I have the derivative 56 e to the 7x as the derivative from that product rule that I'm using on the term 56x times e to the 7x. So again, just these two expressions alone, the sum of those expressions is representing the derivative of 56x e to the 7x. Then the derivative of 8 times e to the 7x would be the derivative of e to the 7x, which is 7e to the 7x times 8, 56 e to the 7x. Now I'm going to multiply 7 times 56, 392. 392 is times x, e to the 7x, and then adding together 56 plus 56e to the 7x, 112 e to the 7x. So that is the answer to the first part. That's what I got for the first part of question of the day, problem 7. Now in the second part, I've got the natural logarithm, which is the inverse of the exponential function base e, and I need to find its derivative, and so I've got to use the chain rule. And so one way that many of my students remember the derivative of the natural log function, and especially if we've got the quotient rule, f prime here of x is going to equal 1 over, and they'll call this inner function u, it will equal 1 over u times the derivative with respect to x of u, and so many of them will say, okay, I'm multiplying 1 over u times du dx. Then some remember the rule for the derivative of the natural log of u this way. Since du dx represents u prime, then they'll say, okay, that's u prime divided by u. So either way you want to remember the formula, that's fine. But 1 over u in this case would be 1 over x cubed plus 3x squared. Then the derivative of x cubed plus 3x squared would be 3x squared plus 6x. I multiply that sum, that is now the derivative, times 1 over x cubed plus 3x squared, and that becomes the rational function that you see there. Now, last but not least, my response to question of the day 8. I'm given the following equation: y times the cosine of x is equal to x squared plus y squared, and I am to find the derivative of y with respect to x. And this notation is real important. You're going to find the derivative of y, and y is to be assumed here to be a function of x. So I'm going to take the derivative operator d dx and apply it to both sides of the equation. The first expression to the left is a product, so I'm going to use the product rule. So y is written down, it's multiplied times the derivative with respect to x of the cosine of x, and notice the argument there of the cosine function is a function of x. Then the cosine of x is multiplied times y. Now y is assumed to be a function of x, but y is not stated explicitly in terms of x. So when I take the derivative of y with respect to x, the only way I can express it is dy dx. I don't know how y is defined in terms of x, and it doesn't make any difference. That is the derivative of that identity of function, the way it's written there, the function y with respect to x. Then I've got to find the derivative of the power function x squared, but this function is in terms of x, its derivative is 2x. However, some function y, which is a function of x, is being squared, so I use the power rule. The derivative of y squared is 2y. But then I have to take the derivative of the base of that function with respect to x. So again, the only way I can state that is dy dx. Now I want to find dy dx, so now I treat this derivative algebraically, grouping together the terms that have dy dx. And so you'll notice here the derivative of the cosine of x is the opposite of the sine of x, so that product is stated as the opposite of y times the sine of x, and the cosine of x times dy dx equals 2x plus 2y dy dx. I group together the terms containing dy dx, so that becomes the cosine of x times dy dx minus 2y dy dx is equal to 2x, and then I add y sine x to both sides, resulting in y the sine of x appearing to the right of the equal sign. Now I'm going to factor, because I'm solving for dy dx, I'm going to factor that expression. It is a common factor from the terms cosine of x dy dx and negative 2y dy dx. So there's the result. That is equal to 2x plus y sine x, and I solve for dy dx by dividing 2x plus y sine of x by the cosine of x minus 2y. So that is my answer to question of the day 8. See if you agree with that. If your results do not agree with mine, or if you have a question about my work, please let me know.